So what we want to look at today is what's called the amplitude, the frequency related to the period, and the phase shift of a trig function. We know what a trig, and I'm going to do most of these based on the sine graph just because the sine graph's an easy one, and it's the first one we developed in class together. And so what you need to realize is that the amplitude is nothing more than the height. When we take a look at our sine function, y equals sine of x, let me write that down. This is y equals the sine of x. And this particular one, when we did it in class, we did it from 0 to 2 pi. But this one goes on, and you can see that this is an oscillating function. It repeats itself over and over and over. And that this function actually oscillates between positive 1 and negative 1. So it starts at 0, it hits 1, it goes back to 0, hits negative 1, 0, 1, 0, negative 1, 0, 1, etc., 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 through the life of that domain. So because of that, the amplitude is actually the difference between the x-axis, which is what we call the midline. Oops. This is called the midline. The x-axis is the line y equals 0. And its peak, its highest point, or the midline and its lowest point, the absolute value. So in a given trig function with no manipulations and no transformations, the amplitude on that, or the height on that, and let me just write that down, that the amplitude is actually equal to the height, or the distance from the midline to the peak. That's the easiest way. And so it's just going to be 1. So if I asked you to graph the function y equals 2 times the sine of x, what I'm asking you to do is to double the ratio at any given value of x. And again, what I'm going to do is I'm going to concentrate on a single interval from 0 to 2 pi. So the regular graph might look like this, from 0 to 1 to 0 to negative 1 to 0, where my amplitude or my height, and this would be at 2 pi and this one would be at pi, would go from 0 to 1. So the highest point is at 1 and the lowest point is at negative 1. If I, however, change my amplitude to 2, what I'm actually doing is, it's kind of like that vertical stretch that we did with all of our other basic functions. Because this is a multiplier on the function, it's like a vertical stretch. So what would happen is it multiplies by every one of the trig ratios. What we concentrate on are the quadrantals, where are the zeros, the ones, and the negative ones. So at 0, the sign is 0, 0. Twice that is still 0. But at 90, here, the sign of 90 is 1. Twice that will be 2. At 180, the sign of 180 is 0, and twice that is still 0. 270, the sign of 270 is negative 1. 2 times that will be negative 2. And then, of course, back to 0. And all the other values in between just fit themselves into that curve. So say at 30, where the sign of 30 would typically be 1/2, if I double that, I'll now be at 1. So when I draw this in, and again, I only worry about where are the zeros, the maxes, and the mins. Those are what I worry about. And then I just sketch it in by doing the best I can. So this one here is going to be y equals 2 times the sine of x. Whereas the black one here, I don't know if I can do this, would be y equals just the sine of x. Okay, so that amplitude of 2 is going to actually stretch that that function vertically, so that instead of peaking out at 1, it'll now peak out at 2. The amplitude always sits right here. We use a as the variable that represents amplitude, very, very befitting. And so it always sits in front of the function. Now, interestingly enough, I can actually give you a function with an amplitude, and I can negate it. So let's say I want a function that says y equals, say, negative 2 times the sine of x. Well, here's the thing. We already know that a negative in front of a function actually reflects that function in the y-axis. And that is exactly what's going to happen to this. The amplitude is still 2, because the amplitude is going to be the distance between the midline and the peak, no matter where that peak is. This negative is actually a reflection in the x-axis, so it's going to be upside down. Now, a lot of people like to think of this as one piece, and so they'll say, okay, sine typically starts at 0, and so even with a negative 2 multiplier, it'll still start at 0. But then at 90, where the sine of 90 is typically 1, if I multiply that by negative 2, I will get my new value. And so this is going to slip down here to negative 2. It'll go back to 0 at 180, or pi. Then it'll go up to positive 2 at 270, and then back down to 0 at 2 pi, 360. So this one is representing y equals negative 2 times the sine of x. Understand, though, that the amplitude is 2, because the distance from the midline to the peak is 2. A lot of people want to say it's negative 2. It's really not. The negative is a reflection. Okay, so and that's what happens. This is a reflection in the x-axis, and that's what turns it upside down, if you will. Okay, the next thing that we want to talk about is the frequency of the graph. And frequency, just from English, you know frequency. How frequent does something happen? The frequency, if I increase the frequency of a sine graph, what it's going to look like is this. So say here's a normal sine graph, okay? And it goes on forever, and I already know that. If I increase the frequency, what that means is that I'm going to increase how quickly it repeats. On and on and on. If I decrease the frequency, I'm going to slow down how often it repeats. Now with sound, a low frequency like the blue line will be a very low tone, whereas the red one, as you increase the frequency, it increases the pitch and it becomes very high. Okay? So the frequency is how often the graph occurs. Okay? The frequency in a trig function is actually going to be a multiplier on the angle. So we will actually be multiplying theta by something. So if theta is normally, let me just throw a number in here, 2x. So if my theta is normally 30 degrees, I would double it first. I'd get 60 degrees and take the sine of 60. If theta is normally 90, then when I double it, I get 180. And the sine of 180 is going to be very different from the sine of 90. Okay, so let's go to the page. And we're going to actually look y equals the sine of x and compare it to y equals the sine of 2x. Okay, so that y equals the sine of x, we already know this is my 2 pi, my pi over 2, and 3 pi over 2. That's a 3. And so if I go to 1 and to negative 1, and this is what my basic graph looks like. Y equals the sine of x. I know that starts at 0. It hits 1 at 90, goes back to 0. It hits negative 1 and back to 0. And if I just sketch that in quickly, this is what I will have. This is what we call one cycle or one period of the graph. Now when I go to this one, twice x, what that means is I'm going to see twice as many sine curves. The frequency is 2. So I need to double the number of sine curves in this interval. And so what's going to happen is if I have to have 2 sine curves between 0 and 2 pi, my first sine curve has to end here at pi. And so that means it's going to zero out at 90, and then it's going to peak at 45 and at 135, and then I'll have another set in here where it'll peak here and it'll bottom out there. So when I double the number of sine curves, that's what I'm going to get. And this is the one for y equals the sine of 2 times x. Well, this brings us to a really important concept called the period. Okay, the period is how long it takes to complete one cycle of the graph. So from 0 to 2 pi, with my red curve, which was my original, y equals the sine of x, the period of that graph is 2 pi, or 360 degrees, 2 pi, because it takes an entire 360 degrees to unwrap and complete that full circle, or unwrap that unit circle, I should say, and complete the full cycle of that graph. But when I increase the frequency to 2, it's going to speed this up, you know, how often this thing oscillates. And so in between 0 and 2 pi, I'm actually going to see 2 full cycles of this graph, which means then the period, it only takes pi radians to complete the cycle once. Okay, so there is an actual formula for period. The period of the graph is equal to 2 pi, which is how long it normally takes to complete one sine graph, and I'm going to divide it by the frequency, f. And so for this graph here, if I take 2 pi and divide it by 2, I will end up with pi, which is exactly where that first graph ended. So this is a really important formula. I need you to put it down big and bold in your notebook and underline it. Period is equal to 2 pi divided by frequency. We're going to be using this formula in 2 directions. If I know the frequency, I can find the period by dividing 2 pi by the frequency. And if I know the period, I can find the frequency by using the same formula. Okay, I'm going to stop there because this video is getting a little bit too long. So in class tomorrow, we're going to look at the graphing one cycle or one period of the graph against graphing it throughout an interval. And we're going to manipulate the amplitude, the frequency, the period, and we're going to look at something called the phase shift. Okay, see you tomorrow.